Section 511 is the concept of limiting reagent. And so basically all reactions are going to have a limiting reagent. Because what's going on here is extremely rare. If you look at it, we have this reaction of nitrogen and hydrogen to make ammonia. And we have 1 nitrogen, 3 hydrogens to make 2 ammonias. And it is balanced. And if you look at the beaker or flask on the left, there's 1, 2, 3, 4, 5 complete reactions that will occur. So we should get 5 times 2 is 10 molecules of ammonia. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Because if you look over here, we got 1, 2, 3, and 1. 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 So it all works out perfectly. But in real life, these atoms are so small, these molecules are so small. When you measure something out, it's nearly impossible to get to be exactly the right ratio. For example, let's say this reaction asked for 1, well, no, not 1, let's say, whatever. Let's say 1 gram of nitrogen, okay? And you measure it out on the best balance that we have in our lab to you have 1.0001 grams of nitrogen. You could say that's basically the same, right? Well, let's look at how different those two values are. The difference between them is approximately 0.0001 grams of nitrogen. The molar mass of nitrogen is 2 times 14.007 or 28.014 grams per mole. So if we take that mass difference, all right, and then we divide it by its molar mass, we can get the moles of nitrogen. And we get 3.57 times 10 to the negative 7th moles of nitrogen. A very, very, very tiny number. 3.5, or I guess just to say 35 billionths, 35 millionths of a mole. But if we take that value, which seems very small, and we convert it to molecules with Avogadro's number. All right, so we have moles of nitrogen, and we multiply it by Avogadro's number, 6.022 times 10 to the 23rd molecules of N2 per mole of N2. I should have canceled out these here. We get an absolutely huge difference. We get 2.14 or 2.15 times 10 to the 18th molecules off. That's 2.15 quintillion molecules off. 2 quintillion molecules off. So insane. In the tiniest amount that you can even get on a balance in an everyday lab. And the ones that can go to 4 decimal places are extremely expensive. And so the tiniest little difference in mass to us is a massive difference in the number of molecules, unfathomably large number of molecules off, that 0.0001 grams of nitrogen. So whenever you measure something in a lab, there's no way to ever get the exact stoichiometric ratio of things. So we have to have this concept called the limiting reagent. And this picture shows exactly what a limiting reagent is. And you can see that now on the left, we have 1, 2, and 3 complete reactions going, because there's in each one nitrogen molecule, 3 hydrogen molecules. So we're going to get 3 sets of products. And since each reaction makes 2 ammonias, we should get 6 ammonias, which we do. We've got 1, 2, 3, 4, 5, and 6. But notice these little guys here in green that I've highlighted. Those are 2 extra nitrogen molecules. And they're unreacted. Okay. So another way of saying it is they are in excess. Okay. What's not in excess are hydrogens. They're all used up. The ones that are all used up in the reactions are called the limiting reagent. Everything else is going to be excess reagent or reagents. An limiting reagent is the reactant that runs out first and thus limits the amount of products that can form. Let's consider the example of nitrogen and hydrogen to make ammonia again. If we suppose that 25 kilograms of nitrogen and 5 kilograms of hydrogen are mixed, how much ammonia is produced, assuming complete conversion? There are 2 ways to solve this. 1, use reactant quantities and mole ratios, and 2, use quantities of products formed. So we have mass of nitrogen. Again, these are in kilograms. Convert these to grams. So we have 25,000 grams of nitrogen. We have the mass of hydrogen is 5,000 grams of hydrogen. And it asks how much ammonia is produced. So we need mass of ammonia right there. So we need the molar mass of all 3 of these compounds. Molar mass of nitrogen is 2 times 14.007, 28.014 grams per mole. Molar mass of H2 is 2 times 1.0079, which is 2.0158 grams per mole. Molar mass of ammonia is 14.007 plus 3 times 1.0079, which comes out to 17.031 grams per mole. All right. So now that we have everything, molar masses and masses, we can do this problem. Okay. So what I know is I have the mass of nitrogen, 25,000 grams of nitrogen. I have to always divide by its molar mass to get it to moles. So I'm going to divide by 28.014 grams of nitrogen per mole of nitrogen. Grams of nitrogen cancel out. And then I need, it says there's 2 ways. Use reactant quantities and mole ratios. So I'm going to leave it at that at this point. And I'm going to go down to the hydrogen. We have 5,000 grams of hydrogen. And that I'm dividing by its molar mass. All right, and grams of hydrogen cancel out. All right, so the next thing is, so this gives you moles of each. All right, and we're going to compare those and compare them to the balanced equation. Okay, so from 25,000 divided by 28.014, you get 892.4 moles of nitrogen. For the second one, 5,000 grams of hydrogen divided by 2.0158 grams per mole is 2,480.4 moles of hydrogen. So you have a heck of a lot, and that's a 0 right there. You have a heck of a lot more moles of hydrogen than we have nitrogen. But if we look at the balanced equation, we need 3 times as much hydrogen as we need nitrogen. Do we have 3 times as much? I don't know. So this is all under the first step. If I erase these and I just go and I do the mole ratio of the reactants, 3 moles. Actually, okay. I'm going to erase just this right there. Okay. So we have 3 moles of hydrogen in the reaction for each single mole of nitrogen. Moles of nitrogen cancel out. And that gives us 2,677.2 moles of H2 needed. Do we have that much? This tells us no. And so therefore, H2 is the limiting reagent, and LR for short. The nitrogen, N2, because it would essentially make more, is the excess reagent. All right, that is the first step to do it. And then after that point, you'd have to go, since it asks for the amount of ammonia that would be produced, we have to do a whole nother thing where we take that 25,000 grams. Oh, no, we don't use that. We use the limiting reagent always. We take the 5,000 grams of hydrogen, divide by its molar mass, multiply by the mole ratio, and ammonia in there was 2. And there were 3 moles of hydrogen. And then finally you multiply by the molar mass of ammonia, which was 17.031. Okay, grams of hydrogen cancel out. Moles of hydrogen cancel out. Moles of ammonia cancel out, leaving us with just grams of ammonia. And we get 5,000 divided by 2.0158 times 2 divided by 3 times 17.031, and you get 28,162.5 grams of ammonia produced. Okay? Now, that was all step 1, or type 1, which is probably the harder way to do it. The other way is to not do it all like this, where I had to like compare the two together and then do a whole nother step. Instead, you just do both together at the same time towards the product, and then you'll be good to go. Okay, and I kind of erased something here. That should be 17.031. So what I'm going to do is just take the 25,000 grams of nitrogen, divide by its molar mass, multiply by the mole ratio, in this case, to ammonia, and then multiply by the molar mass of ammonia, grams of nitrogen cancel out, moles of nitrogen cancel out, moles of ammonia cancel out, leaving us with grams of ammonia. So this would give us 25,000 divided by 28.014 times 2 times 17.031, 30,397.3 grams of ammonia. You might remember before, if it was hydrogen, it was like 28,000 something. And so you could just do it like this. Just take each of them to the product and see which one gives you the least amount. All right, so same basic calculation, but using everything from the balanced equation. And from this, just as a reminder, all in one step, you get 28,162.5 grams of ammonia. So therefore, again, you have in that process of doing these two different reactions, you get the limiting reagent is hydrogen because it makes less product, and the mass of the product that you get is already there for you, 28,162.5 grams. Now, significant figures would be the next step, 5,000 grams, which in the problem had 3 significant figures. The answer would be to 3. So actually this would be 28,200 grams of ammonia. Example 517 on page 234. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. So we're going to make nitrogen gas by passing ammonia over copper 2 oxide, which would be CuO, at high temperatures. The other products of the reaction are solid copper and water vapor. All right, so there's our skeleton equation. Now we need to balance it. So we have 2 nitrogens, which means we need 2 nitrogens there. And we have 6 hydrogens on the left now, 2 on the right. If we put a 3 in front, that gives us 3. We have 3 oxygens on the right, which means we need 3 there and 3 there. So there's our balanced equation. The question says, if a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, Which is the limiting reactant and how many grams of nitrogen are formed? So, we have everything there. First step, what is the limiting reactant or limiting reagent? And so we have we have to have the molar masses of these three. These ones don't matter. All right, so ammonia, which we just did in the previous slide, is 17.031 grams per mole. The molar mass of copper 2 oxide is going to be 63.546 plus 15.999. Comes out to 79.545 grams per mole. And the molar mass for nitrogen is 14.007 times 2, or 28.014 grams per mole. All right, so now I'm going to take that 18.1 grams of ammonia, convert it to the mass of nitrogen, and we get so we take the mass of it, we divide by its molar mass, which was 17.031. Then we multiply by the mole ratio, 1 mole of nitrogen for every 2 moles of ammonia. And then we multiply by the molar mass of nitrogen, which is 28.014 grams of nitrogen per each mole of nitrogen. All right, so grams of ammonia cancel out, moles of ammonia cancel out, and moles of nitrogen cancel out, and we get 14.9 grams of nitrogen. Now, it should be the 3 significant figures because the conversion factor is always infinity, and then we've got 5, 5, and 3 for the significant figures. All right, next one I'll do in blue. We have the 90.4 grams of copper 2 oxide. It's being divided by 79.545. And the mole ratio here is 1 mole of nitrogen for every 3 moles of the copper 1 oxide or copper 2 oxide. And then we multiply again by the molar mass of nitrogen. All right, so grams of copper 2 oxide cancel out. Moles of copper 2 oxide cancel out. And moles of nitrogen cancel out, leaving us with a mass of 10.6 grams of nitrogen. So what we need to do is compare these values here, and you just pick the smaller one. The mass of nitrogen formed is 10.6 grams. Okay, so our answer is the one in green. Our limiting reagent is therefore the copper 2 oxide. So these are our answers for that.